Look up at the night sky and it feels like you are seeing everything. An endless dome of stars scattered across the darkness, whispering that you are small and the universe is huge. It is comforting and a little terrifying at the same time. Yet almost everything you are seeing is a lie of scale. Your eyes are not showing you the universe. They are showing you a wafer-thin layer of our own galaxy and almost nothing beyond it. Tonight we are going to peel that illusion away and step out into our real neighborhood, a hidden family of galaxies that quietly shapes our fate. If you enjoy journeys that stretch your sense of scale, tap like, subscribe, and come explore the universe next door with us. Start with a simple question. When you stand outside under a clear sky, how much of the universe are you actually seeing? Not in photographs, not through giant telescopes, just with your own eyes. The honest answer is, almost none. Nearly every star that you can see without a telescope is part of a single system, the Milky Way galaxy, a rotating disk of hundreds of billions of stars wrapped in an invisible halo of dark matter. Your whole life, your whole planet, every ancestor who ever looked up has lived inside this one star city without ever stepping outside it. That fact alone is already humbling, but the illusion goes deeper. Our galaxy itself is not alone. It belongs to a small, gravitationally bound family of galaxies called the local group. Picture a kind of island chain in space, stretching over roughly 10 million light-years. At the centre of this chain sit two giant spirals, our Milky Way and a slightly bigger neighbour that we will meet properly later. Around them swarm dozens of smaller galaxies, dim and fragile, many of them invisible even in long-exposure photographs taken from Earth. This entire structure, from one side to the other, would fit easily inside the much larger web of galaxies that fills the observable universe. Our senses have no chance of grasping that on their own. Human eyes evolved to judge whether the fruit on a tree is within reach, not to compare the sizes of galaxies separated by millions of light-years. On a dark night, you might see a few thousand stars. It feels like a lot, yet compared to the hundreds of billions of stars in the Milky Way, that is like trying to understand an ocean after staring at a single cup of water. The sky feels vast because your brain has nothing to compare it to. Without numbers, without maps, without physics, your tiny sample of stars masquerades as the whole universe. So astronomers had to cheat. They built tools that stretch our senses across distance and time. Telescopes that gather more light than your eyes ever could. Spectrographs that split that light apart to reveal the fingerprints of elements. Detectors that can stare at one patch of sky for days, stacking faint photons until dim galaxies emerge from the noise. With those tools, they started to notice something strange. Some of the little smudges on photographic plates were not clouds or gas inside our galaxy. They were whole other galaxies entirely, each one a separate city of stars, some orbiting our own. Slowly, a new picture formed. Our Milky Way is not the universe. It is not even a particularly special part of the universe. It is one major member of a modestly sized group. The local group is home to perhaps 50 or so galaxies. A few of them are fairly large. Many of them are tiny dwarfs that barely hold themselves together. All of them are linked by gravity, locked in a slow cosmic dance. They tug on one another, steal stars and gas, and will eventually collide and merge. To them, our sun and planets are an almost meaningless detail. Think of the observable universe as a kind of cosmic Earth. In that picture, a massive cluster of thousands of galaxies might be a continent. A great filament of galaxies that stretches for hundreds of millions of light-years might be an ocean crossing trade route. The local group is not a continent and not a nation. It is more like a small town, a loose association of star cities living on the outskirts of larger structures. Our home galaxy is just one house in that town. When you stare at the night sky, you are mostly looking at the walls and lights inside that one house, with perhaps the faint glow of a neighbour leaking in through a window. The twist is that this little town still controls almost everything that matters for us. The shared gravity of the Milky Way, its large neighbour, and the surrounding dwarfs keeps us bound together over billions of years. Their mutual pull defines the path of our galaxy through space. Their future collisions will reshape the sky our descendants see. Even the invisible dark matter halos of these galaxies overlap and interact, creating a shared gravitational well that steers the orbits of stars, gas, and everything built from them, including us. So the story of the universe is far too big to tell all at once, but we can start with something more manageable. We can start with our neighbourhood. In the parts that follow, we will tour the major members of the local group, from giant spirals to faint dwarfs. We will see how they formed, how they interact, and how they will eventually collide. Along the way, we will discover that what looks like a peaceful scattering of stars above your head is actually the surface of a vast, dynamic structure. A structure that has been quietly writing the future of our sky for billions of years, and will keep doing so long after our little planet has finished its brief turn under the stars. To understand our cosmic neighbourhood, we have to start at street level. In this case, that means our own galaxy. The Milky Way is not just a pretty band of light in the sky. It is a rotating star city with structure, order, and traffic patterns. Instead of cars and highways, it has stars and spiral arms. Instead of skyscrapers, it has dense clusters and a crowded central district where gravity rules with an iron grip. Picture the Milky Way as a huge, thin disk of stars and gas, with a bright bulge in the centre. The disk is about 100,000 light-years across, yet only roughly 1,000 light-years thick in most places. If you turned it on its side, it would look like a glowing coin floating in space, with a thicker lump in the middle where the bulge sits. Our Sun is not in that central bulge. It lives out in the suburbs, roughly 26,000 light-years from the centre, tucked into a minor feature called the Orion Spur, between two larger spiral arms. That position matters. Being out in the disk rather than in the core gives us a relatively calm environment. There are still supernova explosions, star-forming regions, and passing clouds of gas, but the density of dangerous events is much lower than in the central bulge. You can think of it as living in a quiet residential district rather than downtown next to a power plant. It is still a big city though. The Milky Way holds hundreds of billions of stars, along with vast clouds of gas and dust that are constantly being recycled into new generations of suns and planets. The Milky Way also has a hidden backbone. Running through the central region is a long, bar-shaped structure of stars. This bar acts like a gravitational conveyor belt, funneling gas toward the centre and helping maintain the spiral arms that sweep outward. These arms are not solid objects. They are waves of higher density moving through the disk, like traffic jams that cause cars to bunch up, even though individual cars move in and out. Where gas and dust pile up in these waves, they collapse into new stars. When you see images of bright blue spiral arms, you are looking at newborn stars lit up along these waves. At the very centre of all this activity sits something much more extreme. Buried in the crowded core of the Milky Way is a supermassive black hole called Sagittarius A star. It contains the mass of a few million suns, compressed into a volume smaller than our solar system. Most of the time it is quiet, feeding only slowly. But the orbits of stars around it reveal its presence in the same way the motion of planets reveals the Sun. This central monster, the bar, the bulge, the disk, and the surrounding dark matter halo, together define the skeleton of our home galaxy. Now lift your eyes from our own city and look outward. About 2.5 million light-years away lies our big neighbour, Andromeda. In long-exposure photographs, it looks serene, a graceful spiral with delicate arms and a bright core. In reality, it is a heavyweight, at least as massive as the Milky Way, and likely more. It stretches roughly 200,000 light-years from side to side. Where the Milky Way feels like a large city, Andromeda is a sprawling megacity, with perhaps around 1 trillion stars. Structurally, Andromeda is a cousin of the Milky Way. It is also a barred spiral galaxy, though its bar is more subtle and harder to see in images. Its disk is thicker and brighter, with prominent dust lanes and star-forming regions that wrap around the core. deep photographs reveal long, faint streams of stars arcing around Andromeda. These are the remains of smaller galaxies that wandered too close and were torn apart. Andromeda has been eating its neighbours for billions of years, and it wears the scars of that ancient cannibalism like faint tattoos. At its heart, Andromeda hides an even more massive black hole than ours. Estimates suggest it contains tens of millions of solar masses. That is a gravity well so deep that not even light can escape once it crosses the point of no return. When gas falls toward this central object, it can heat up and shine, sometimes creating brilliant active phases in a galaxy's life. Andromeda is relatively quiet now, but its central black hole is still there, an invisible engine waiting for its next meal. Then there is the third member of this big three, the Triangulum galaxy, also known as M33. On paper, Triangulum is the lightweight of the group. It is smaller, with perhaps a few tens of billions of stars, and it lacks the big central bar seen in its larger cousins. It is a pure, graceful spiral with open arms and a less prominent bulge. If the Milky Way and Andromeda are vast capital cities, Triangulum is more like a vibrant regional town. Do not let the lower mass fool you. What Triangulum lacks in sheer scale, it makes up for in energy. It is one of the most actively star-forming galaxies in the local group. Its disk is dotted with bright, hot, young star clusters and enormous glowing clouds of hydrogen gas that mark stellar nurseries. When astronomers take detailed images, they see knots of light that are some of the largest star-forming regions known, places where thousands of new suns are being born in loose clusters. Seen side by side, these three galaxies tell a story about variety and family resemblance. All three are spiral galaxies. All three have rotating disks, spiral structure, and central concentrations of stars. Yet their sizes, masses, star formation histories, and central black holes differ. They are like three cities built to the same basic plan, but at different scales, with different populations and different industrial districts. The photographs can be deceptive. Long exposure images taken by space telescopes make these galaxies look calm and eternal. Soft spirals, gentle glows, aesthetic objects for wallpapers and posters. Beneath that calm surface though, each one is violent on cosmic timescales. They swallow dwarf galaxies, trigger bursts of star formation, blast gas into space with supernova explosions, and reshape themselves over billions of years. The majestic spiral arms are scars of this ongoing drama. When you picture the local group now, do not imagine a random collection of blobs. Imagine a small town in which two giant cities, the Milky Way and Andromeda, dominate the skyline, and a smaller but fiercely productive Triangulum glows nearby. Around them swarm many smaller settlements that we will meet later. Their gravities overlap, their histories intertwine, and their futures are already linked. In the next part, we will leave the grand avenues of the Big Three and head into the back roads, where the tiny dwarf galaxies hide the deepest clues about dark matter and the early universe. So far we have talked about the glamorous residents of the local group, the giant spirals that dominate the photographs and the headlines. If the Milky Way, Andromeda and Triangulum are the bright city centres, the natural next question is simple. What about everything else? What are most galaxies actually like? The surprising answer is that most galaxies are nothing like the Big Three. They are smaller, dimmer, and easier to miss. In fact, the local group is ruled by a quiet majority of tiny galaxies that barely show up at all. Astronomers call them dwarf galaxies. The word dwarf makes them sound cute, but these are serious players in the story of the universe. A dwarf galaxy might have only a few million stars, or even just a few tens of thousands, compared to hundreds of billions in a large spiral. Their sizes can be only a few thousand light-years across. If you could hold the Milky Way and a typical dwarf side by side, the big galaxy would look like a sprawling metropolitan area, while the dwarf would be a small town with a handful of streets lit up at night. These small towns come in different flavours. One family is the dwarf elliptical galaxy. These look like tiny, smooth blobs of light with no obvious structure. They are round or slightly stretched, with stars moving in all directions rather than in a neat rotating disk. Closely related are dwarf spheroidal galaxies. As the name suggests, they are even more diffuse and spheroidal, often stretched by the gravity of a larger neighbour. Both types usually have very little gas left and almost no ongoing star formation. Their light comes mainly from old reddish stars that have been shining for billions of years. Then there are the oddballs, the dwarf irregular galaxies. These are messy, asymmetrical collections of stars and gas, without clear spiral arms or bulges. They often still form stars, sometimes in scattered clumps where gas has managed to stay dense enough to collapse. The large and small Magellanic Clouds that hang in the skies of the southern hemisphere are famous examples on the border between dwarfs and more massive irregulars. Smaller cousins hide all over the local group, sometimes trailing streams of gas as they move through the halos of bigger galaxies. If these dwarfs are so common, why did we take so long to notice them? The answer lies in something called surface brightness. A large, bright galaxy concentrates a lot of light into a relatively compact area. A typical dwarf spheroidal spreads a tiny amount of light over a relatively large patch of sky. Even if it is nearby, it can be almost invisible, like a faint fog against the darkness. On early photographic plates and even on many modern images, these galaxies vanish into the background unless you look with extreme care. To find them, astronomers had to get clever. Wide-field surveys that image huge portions of the sky, combined with digital detectors and powerful computers, allowed them to search for subtle overdensities of stars. Instead of a single bright patch, they looked for a slight statistical excess of faint stars moving together. That is how many of the smallest known galaxies around the Milky Way and Andromeda were discovered. As surveys improved, the census of dwarfs in the local group kept going up, and there is every reason to think we are still missing many of them. These unassuming galaxies carry one of the biggest secrets in cosmology. They are dominated by dark matter. Dark matter is the name we give to whatever invisible mass is providing extra gravity in the universe. We cannot see it directly, but we can measure its pull. In large galaxies, we infer dark matter from the way stars and gas orbit. In dwarf galaxies, the effect is even more dramatic. The stars move as if there is far more mass present than their faint light would suggest. When astronomers measure the speeds of stars inside dwarf spheroidals, they find that the visible mass is only the tip of the iceberg. For every unit of mass in stars, there can be hundreds of units of dark matter. In some of the most extreme ultra-faint dwarfs, there may be thousands of times more dark matter than ordinary matter. These systems are almost pure dark halos, with a sprinkling of stars, like a few fireflies trapped inside a vast, invisible glass sphere. This makes them perfect natural laboratories for studying the properties of dark matter. Why do dwarfs end up this way? Part of the answer is that their gravity wells are shallow. It does not take much energy to throw gas out of a small galaxy. When the first generations of massive stars in a dwarf galaxy explode as supernovae, they pump energy into the surrounding gas. In a big galaxy like the Milky Way, that gas might be jostled and heated, but eventually cools and falls back to form new stars. In a tiny dwarf, many of the gas atoms are simply kicked out into space, never to return. The early universe added a second punch. A few 100 million years after the Big Bang, the first stars and galaxies flooded space with high-energy ultraviolet light. This era, called reionization, turned much of the diffuse hydrogen gas into a thin, electrically charged plasma. For large galaxies with deep gravitational wells, that was an annoyance. For the smallest dwarfs, it was disaster. The warm, ionized gas was too energetic to collapse back into their shallow halos. Star formation in many of these systems shut down after only a short initial burst. The result is that many dwarf spheroidal galaxies in the local group are almost pure fossils. Their stars formed more than 10 billion years ago and then stopped. The stars we see in them today are relics from a time when the universe was still young, carrying in their chemical compositions the signatures of the very first supernovae. When astronomers analyze their light, they find that these stars are extremely metal poor, meaning they contain very small amounts of elements heavier than hydrogen and helium, That is exactly what you would expect if just a few early generations of massive stars enriched the gas before everything shut down. Each dwarf tells a slightly different story. Take a brighter system like the Fornax dwarf. It has several globular clusters, dense balls of old stars, which suggests it was once more massive and held onto its gas longer, forming stars over an extended period. A fainter object like the Sculptor dwarf shows a sharper cutoff in its star formation history, hinting at an early quenching, possibly by reionization. In even smaller, ultra-faint dwarfs, almost all the stars belong to a single ancient population, like a snapshot of the cosmos frozen in time. Beyond their individual histories, these galaxies are crucial tests for our ideas about the universe as a whole. The leading model of structure formation, often called cold dark matter, predicts that large galaxies like the Milky Way should be surrounded by many small dark matter halos. For a long time, simulations produced far more small halos than the number of known dwarf galaxies, a puzzle sometimes called the missing satellites problem. The discovery of many ultra-faint dwarfs has reduced that tension, but it has not eliminated the mystery. It suggests that many small halos may either never form stars, or do so only briefly and weakly. Dwarf galaxies also probe how dark matter behaves in their centers. Simple models predict a steep increase in density toward the middle, a sharp cusp. Some observations, however, hint at flatter central regions called cores. One idea is that repeated bursts of star formation and supernova feedback can stir the dark matter and soften the cusp. Another possibility is that our basic assumptions about dark matter are incomplete. In either case, the answer is hidden inside these tiny local group galaxies that you will never see with your eyes, but that dominate the census of structures around us. So when you imagine the local group now, do not picture only a few grand spirals floating in empty space. Picture a swarm of small companions, most of them invisible without powerful telescopes, drifting in and out of the halos of the giants. They are fragile, easily torn apart, and yet stubbornly informative. They tell us how the first stars lived and died, how galaxies formed from the bottom up, and how an invisible form of matter shaped everything we see. In the next part, we will follow these dwarfs into the danger zone, where the gravity of larger galaxies begins to tear them to pieces and scatter their stars across the sky. If dwarf galaxies are the quiet majority of the local group, some of them live in the loudest possible neighborhood. They orbit right next to the giants. These are the satellite galaxies, small systems that spend their entire lives inside the extended halos of big galaxies like the Milky Way and Andromeda. The question is simple. What happens when something so small spends billions of years next to something so massive? The answer is not peaceful coexistence, it is slow violence. Take the Large Magellanic Cloud. If you stand under dark southern skies, you can see it with your naked eye as a faint, fuzzy patch. It is a dwarf galaxy, but a hefty one by dwarf standards, with its own bar of stars and vigorous star formation. Nearby in the sky is the Small Magellanic Cloud, a slightly smaller companion. For a long time, astronomers thought these two had been calmly orbiting the Milky Way for ages. Now the evidence points to a more dramatic story. They are probably on their first proper plunge into our halo, falling inward along a long orbit that may one day end in a merger. You can already see the strain. Radio observations reveal a long ribbon of gas called the Magellanic Stream trailing behind them, stretched out for hundreds of thousands of light years. That stream is gas pulled away by the Milky Way's gravity and by the pressure of the hot halo gas our galaxy sits in. It is as if the Magellanic Clouds are speeding through a thin, invisible atmosphere, their outer layers being stripped off to form a tail. Within the clouds themselves, tidal forces tug on stars and gas, distorting their shapes and stirring up new bursts of star formation. Move closer to the Milky Way, and the situation gets even more extreme. The Sagittarius dwarf galaxy is one of the clearest examples of a satellite in its final act. It is a small, elongated system that plunges right through the disk of the Milky Way on a polar orbit. Each time it passes near the centre, our galaxy's gravity pulls more stars and dark matter away. Over many orbits, this slow theft has stretched Sagittarius into long streams of stars that wrap almost all the way around the Milky Way. We can actually see these streams in surveys of the sky. They appear as great arcs of stars that share common motions and chemical fingerprints. To the naked eye, the Milky Way's halo looks like a smooth glow. In detailed data, it is laced with these streams, the ghostly remains of shredded dwarfs. Sagittarius is only the most obvious example. There are other streams with names like Orphan and GD1 that likely share similar origins in destroyed satellites, whose cores may no longer even exist as separate objects. Then there are satellites that look oddly rich for their size. The Fornax dwarf galaxy, for instance, orbits the Milky Way at a comfortable distance, far out in the halo. It is not particularly bright, yet it hosts several globular clusters. Globular clusters are dense, spherical gatherings of hundreds of thousands of old stars. In a galaxy as massive as the Milky Way, having many of them is not surprising. In a small dwarf, the presence of several clusters suggests that Fornax used to be more massive and vibrant than it appears today. Fornax seems to have formed stars for a long stretch of cosmic time before something shut the process down. Its stars show a range of ages and chemical compositions, evidence of repeated cycles of star formation and enrichment. Today, though, it looks faded, with little or no gas left. Tidal forces and interactions with the Milky Way's halo gas likely stripped away much of its fuel and perhaps some of its dark matter, reducing it from a more imposing system to the modest dwarf we see now. Contrast that with the Sculptor dwarf galaxy, another Milky Way satellite. Sculptor is dominated by very old, metal-poor stars. Its star formation apparently ended early, perhaps helped along by reionization and later by environmental effects from the Milky Way. Where Fornax looks like a small city that stayed busy for a long time before declining, Sculptor is more like a settlement that burned bright very early and then went quiet. Both now orbit under the same giant, but their paths to that fate were different. Our neighbour Andromeda tells a similar story with its own satellites. Two of its most famous companions are known as M32 and M110. M32 is a compact, bright little galaxy right up against Andromeda's disk in the sky. It looks like a tiny, dense ball of stars, much more concentrated than a typical dwarf spheroidal. One leading idea is that M32 was once a larger galaxy whose outer regions were stripped by Andromeda's gravity, leaving only a tight, battered core. M110 is more extended and diffuse, a dwarf elliptical with its own population of old stars and a smoother light profile. Together with other faint companions, these galaxies trace out the gravitational influence of Andromeda's halo. Many show signs of distortion in their shapes and unusual distributions of stars. Some appear to lie along vast plains, suggesting past group infall, where several dwarfs fell into Andromeda's halo together and are still, in a sense, falling as a loose pack. What all these cases have in common is the role of environment. A dwarf galaxy in deep space can evolve in relative isolation. A dwarf galaxy inside the halo of a giant lives under constant stress. As it orbits, tides stretch it, compress it, and can strip away stars and dark matter. Motion through the hot, thin gas that surrounds the big galaxy can blow out its own gas, like wind ripping leaves off a tree. Over time, this combination of gravitational harassment and headwind can transform a once gas-rich, star-forming dwarf into a gas-poor, quiescent spheroidal system. For the stars inside these satellites, the story is even more intimate. Each star is born inside a galaxy with its own chemical flavour, shaped by the particular pattern of supernova explosions and gas flows in that small system. When the dwarf is eventually torn apart, those stars do not vanish. They are added to the halo of the larger galaxy. Their orbits still remember their original paths. Their chemistry still carries the imprint of the smaller world they came from. By measuring both motion and composition, astronomers can work backward and identify which halo stars are the orphans of destroyed satellites. This is how we know that the halos of big galaxies are built, piece by piece, from many such mergers and disruptions. The Milky Way's outer regions are a patchwork of these contributions, each stream and clump a memorial to a lost dwarf. Andromeda, with its enormous and messy halo, shows the same process on an even larger scale. The smooth, idealized spirals in textbooks leave out this gritty, ongoing act of cannibalism. The striking thing is that none of this feels dramatic on human timescales. These satellites take billions of years to complete orbits. Each pass peels off only a fraction of their mass. From our perspective, they appear frozen in a slow dance. Yet over enough time, the outcome is inevitable. Many of the satellites we see today are already doomed. Their orbits will decay, their gas will be stripped, their stars will be scattered into streams and shells. Only careful measurements, long after the fact, will reveal that they ever existed as separate galaxies at all. In the next part, we will step away from the danger zone around the giants and look outward to dwarfs that drift in the quieter spaces between major galaxies, and to the faintest of all, tiny galaxies so star-poor that they blur the line between galaxy and star cluster. There, in the outskirts and in the almost invisible, we find some of the oldest and most pristine relics of the early universe. Not every small galaxy lives under the shadow of a giant. Some slip through the spaces between big galaxies, far from the strongest tidal forces, like lonely islands between continents. Others are so faint that even when they are nearby in cosmic terms, they are almost impossible to see. Together, these isolated and ultra-faint dwarfs show us what happens when the universe builds galaxies in slow motion and then leaves them almost untouched. Imagine pausing the local group and zooming out. You would see the Milky Way and Andromeda as two main hubs, linked by a loose bridge of smaller systems. Between them, and beyond them toward the edges of the group, drift galaxies that are not tightly bound to either giant. They feel the pull of the whole local group, but no single big galaxy dominates their lives. These are the isolated dwarfs, living in the outskirts where gravity is weaker and traffic is light. One of these is IC10. It is a compact, irregular dwarf on the fringe of the local group. Unlike the faded, gas-poor satellites hugging close to giants, IC10 is buzzing with star formation. It has many young, massive stars, and strong winds and outflows from supernova explosions. It looks chaotic and lively, a small galaxy in the throes of a star-forming episode. The lack of a nearby giant means it has held on to enough gas to keep forming stars with gusto. Not far away, in cosmic terms, is IC 1613. It is another isolated dwarf, but with a very different personality. Its shape is more regular, its star formation calmer. Its stars span a wide range of ages, suggesting a more gentle, extended history. Where IC10 feels like a town experiencing a sudden boom, IC 1613 is more like a small city that has been quietly occupied for billions of years, building its population at a steady pace. Then there are the Sextans galaxies in the outskirts, examples of dwarfs that sit at the edge of the local group's gravitational reach. Their orbits and velocities suggest that they are loosely bound to the group as a whole, rather than to any single giant. In these places, far from the dense halos of the big spirals, gas can linger longer. Star formation can proceed in fits and starts, interrupted only by internal processes like supernova feedback, rather than by the harsh environment near a massive neighbour. These isolated dwarfs are important because they give us a baseline. They show what dwarf galaxies can look like when environment is gentle. By comparing them with satellites that have been stripped and harassed, astronomers can separate the effects of internal physics from external forces. If two galaxies have similar starting masses, but very different surroundings, their different fates become a kind of natural experiment, revealing how much gravity, gas, and dark matter each contributes to the final shape. Yet even these are not the faintest actors in the story. To meet the most extreme dwarfs, we have to turn the lights way down. Ultra-faint dwarf galaxies are the dimmest, least luminous galaxies we know of. Some contain only a few hundred or a few thousand stars in total. If you could float inside one and look around, the sky would not be crowded like in the Milky Way. It might look more like a sparse countryside, with lonely stars separated by vast stretches of darkness. Segway 1 is one of the poster children for these systems. It orbits the Milky Way, but it is so faint that it was only discovered in the 21st century through careful analysis of sky survey data. Astronomers found a slight excess of stars in a certain patch of sky, then confirmed that those stars shared similar motions and compositions. When they measured how fast the stars were moving inside Segway 1, they realized that the visible mass could not possibly hold them together. The speeds implied a dark matter halo, hundreds or thousands of times more massive than the stars themselves. Another example is Willman 1, a tiny, diffuse grouping of stars that again appears to sit inside a massive dark halo. These ultra-faint dwarfs are right at the edge of what we can confidently call galaxies. A star cluster, by contrast, is a group of stars bound by their own gravity, but without a dominant dark matter component. In an ultra-faint dwarf, dark matter does most of the binding. The few stars present are tracers, glowing breadcrumbs that reveal the shape of an otherwise invisible structure. Their stars also tell an ancient story. When astronomers take spectra of stars in these ultra-faint dwarfs, they find extremely low levels of heavy elements. That suggests that only a small number of supernovae ever exploded there, enriching the gas just a little before star formation stopped. Many ultra-faint dwarfs seem to have formed most of their stars more than 12 or 13 billion years ago. After that, reionization and their shallow gravity wells likely prevented new gas from cooling and condensing. They are, in effect, fossil galaxies from the first billion years of cosmic history. Finding these systems is a challenge. Their light is so weak and spread out that even modern surveys barely pick them out above the background. Upcoming deep surveys will probably reveal more, and every new discovery will refine our understanding of how many such halos exist and how many manage to form stars at all. It is entirely possible that for every ultra-faint dwarf we see, there are several more that contain so few stars that they are effectively invisible, dark halos wandering the local group unseen. These isolated and ultra-faint dwarfs reshape how we picture our neighbourhood. The local group is not just a few big galaxies with a sprinkling of satellites. It is likely teeming with small dark matter halos, only some of which glow with stars. Where conditions are right and gas can cool, a small halo becomes a dwarf galaxy. Where conditions are harsher, a halo may remain dark. The border between galaxy and dark structure blurs at these scales, and the local group becomes a laboratory for understanding that border. From a human perspective, there is something strangely moving about these tiny systems. The Milky Way and Andromeda will collide and merge in the far future, reshaping the sky in grand, obvious ways. Isolated dwarfs on the outskirts may never notice. The universe will expand, distant structures will slip beyond the cosmic horizon, and yet some of these little islands will keep orbiting quietly, preserving in their sparse stars a memory of the early universe long after more dramatic events have faded. In the next part, we will zoom back out and climb the hierarchy again, placing the entire local group within even larger structures. We will see how galaxy groups, clusters, and superclusters fit together, and how the gravity of distant giants and invisible dark matter continues to pull on our modest neighbourhood, steering it through an ever-changing cosmic landscape. By now, our local group feels almost familiar. You know the big spirals, the dwarfs, the satellites being torn apart. It is tempting to think of this as the whole story, a self-contained little island of galaxies drifting through empty space. That is comforting, and very wrong. The local group is not an isolated bubble. It is one knot in a vast cosmic web, pulled and pushed by structures so huge that even our galaxies become small pieces in a larger pattern. Think about how we organise space on Earth. You live on a street, in a town, in a region, inside a country, on a continent. Each level adds a larger context without erasing the smaller one. The universe does something similar. A star system sits inside a galaxy. Galaxies clump into groups. Groups gather into clusters. Clusters line up along filaments that weave through even larger regions we call superclusters. When we talk about the local group, we are only one step up from the galactic scale. Above us, the hierarchy continues. A galaxy group, like our local group, is a handful to a few dozen galaxies bound together by mutual gravity. In our case, two big spirals, one medium spiral, and a crowd of dwarfs share a common dark matter envelope, roughly 10 million light-years across. A galaxy cluster is the same idea pushed to an extreme. Instead of a few big galaxies, a cluster can hold hundreds or thousands of them, packed into a volume only a few times larger than a typical group. Between the bright galaxies, there is a sea of hot gas glowing in X-rays, and a deep pool of dark matter holding the whole thing together. Our nearest major cluster neighbour is the Virgo cluster. It lies about 50 to 60 million light-years away in the direction of the constellation Virgo. In a telescope, Virgo is a swarm of galaxies, ellipticals and spirals, piled together on the sky. The cluster contains enough mass that its gravity tugs noticeably on the local group, even across that immense distance. You can picture the local group sitting on the outskirts of a metropolitan region dominated by the Virgo cluster, like a small town drawn toward a huge city by shared roads and economic ties. For a long time, astronomers thought in terms of a Virgo supercluster, with our local group as one of many groups arranged around the central Virgo cluster. More recent work has refined that picture into something with an even grander name, Laniakea, which means immense heaven in Hawaiian. Laniakea is a region of space hundreds of millions of light-years across, within which galaxy motions are dominated by a shared pattern of flows toward a central basin of attraction. The local group, Virgo, and many other structures are all falling along this pattern, like water draining toward the same valley in a landscape. The funny thing is that this landscape is almost invisible. We map it not by seeing the mass directly, but by measuring how galaxies move relative to the general expansion of the universe. On large scales, space itself is stretching, and most galaxies recede from each other. That steady expansion is called the Hubble flow. On top of that smooth trend, local gravity makes galaxies deviate from the flow. Some fall together, others are slowed down or sped up depending on the mass around them. By measuring those deviations, astronomers infer where the hidden hills and valleys of mass must lie. One of the most intriguing of those hidden regions is called the Great Attractor. In maps of galaxy motions, many systems in our part of the universe seem to be drifting toward a region in the sky behind the dense plain of the Milky Way. Dust and stars in our own galaxy block our direct view, so for years, the Great Attractor was literally a blind spot, a gravitational pull without a clear, visible source. Deeper surveys have revealed clusters and superclusters there, and farther out another massive concentration, called the Shapley supercluster, all contributing to the drift of galaxies in our neighbourhood. The local group is part of this flow. Relative to the cosmic microwave background, the faint afterglow of the Big Bang, our entire group is moving at roughly 600 kilometers per second, which is over 1,300,000 miles per hour. That speed is hard to feel, because everything around us shares the motion. The sun, the earth, every atom in your body, all surfing together on a river of space, being pulled toward distant masses. From our perspective, the universe looks almost static. In reality, we are plunging through an invisible current. Where did this structure come from? Wind the clock back to a few 100,000 years after the Big Bang, and the universe was astonishingly smooth. Tiny ripples in density, only a few parts in 100,000, are imprinted on the cosmic microwave background. Gravity took those tiny differences and amplified them over billions of years. Slightly denser regions pulled in more matter, grew denser still, and eventually collapsed into the first dark matter halos and galaxies. Less dense regions were emptied out and became cosmic voids. The result is a web of filaments, clusters and groups spanning the observable universe. Dark matter is the scaffolding of this web. It does not interact with light, so we cannot see it directly, but its gravity shapes everything. Ordinary matter, the kind that forms stars and planets and people, falls into the potential wells carved by dark matter. Galaxies light up at the crossroads of filaments, where many streams of matter converge. Galaxy groups like ours sit on these crossings, strung like beads along larger structures. Clusters form where several filaments intersect and concentrate even more mass. On these scales, the local group is both unremarkable and precious. Unremarkable because groups like ours are common building blocks of the cosmic web. Precious because this is the environment that made our existence possible. The local group sits far enough from the centre of a massive cluster that we are not constantly bombarded by cluster-wide violence, yet close enough to feel the long-range pull of the larger structure. Our galaxies have had time to grow disks, form multiple generations of stars, and keep their gas long enough for planets and life to emerge. Emotionally, there is a strange comfort in knowing this. The night sky can feel still, a fixed backdrop to human drama. The truth is the opposite. Our entire neighbourhood is in motion, falling toward distant superclusters, sliding along dark matter filaments, woven into a structure that stretches beyond anything we can directly see. We are passengers in a galaxy that is itself a passenger in a group, a cluster, a supercluster, all caught up in the slow choreography laid down by tiny ripples in the early universe. In the next part, we will zoom back down inside individual galaxies again. We will peel apart their internal structure into bulges, disks, halos, and dark matter, and see how those pieces fit together to make the star cities that populate this vast, gravitational sculpted web. We have talked a lot about galaxies as if they are single objects, a spiral here, a dwarf there, each one a dot on a map of the local group. Now it is time to zoom in and take one apart. Inside a galaxy like the Milky Way or Andromeda, there is a hierarchy of structures: bulges, disks, halos, clusters, clouds. Each one plays a role in how stars are born, how they move, and how they eventually die. A galaxy is not just a pretty pinwheel, it is a layered machine. Start with the disk, because that is where we live. In the Milky Way, the disk is a thin, rotating sheet of stars and gas. Hundreds of billions of suns orbit around the centre in almost circular paths, like cars on many overlapping ring roads. The entire disk spins once every few 100 million years, which means since the Earth formed, it has only made a handful of full laps. When you look up at the band of the Milky Way in the night sky, you are seeing along the plane of this disk from the inside, peering through thousands of light years of stars and dust. The disk is not just a featureless sheet, it has structure. Spiral arms are waves of higher density that wind around the galaxy. They are not solid arms glued to the disk, more like slow-moving traffic jams that stars and gas pass through. When clouds of cold gas enter these regions of higher pressure, they can collapse into new stars. That is why spiral arms glow with blue light from hot, young stars, and with pinkish nebulae where hydrogen gas is lit up by intense ultraviolet radiation. The arms mark where the galaxy is most actively making the next generation of suns. Dig a little deeper, and you find that the disk itself has layers. In the Milky Way, there is a thin disk and a thick disk. The thin disk contains most of the gas and many of the younger stars, including the Sun. It is relatively flat and cool in a dynamical sense. The thick disk is puffier. Its stars move on more inclined and wobbly orbits and tend to be older and poorer in heavy elements. Andromeda shows a similar split, though with its own unique details. These two components hint at a formation history that involved early heating events, such as mergers, followed by a more settled phase of disk growth. At the centre of many spiral galaxies sits a bulge, a ball or bar-shaped concentration of stars. In the Milky Way, the bulge is actually a barred structure, a thick, elongated region of stars that cuts through the inner disk. Stars in the bulge move in more random directions than disk stars do. It is a crowded, dynamic inner city compared to the calmer suburbs of the outer disk. Andromeda's bulge is even more prominent, a bright central glow that dominates many photographs. Triangulum, by contrast, has only a small central concentration. It is more of a pure disk system, which makes it a useful counterpoint when comparing galaxy architectures. Wrapped around all of this is the stellar halo. If you could turn down the brightness of the disk and bulge, a faint, roughly spherical cloud of stars would emerge, extending far beyond the visible disk. These halo stars are sparse, old, and often on highly elongated or inclined orbits. They do not care much about the plane of the disk. They wander above and below it, tracing paths that carry them far from the galactic centre and then back again. Embedded in this halo are globular clusters, some of the oldest and most tightly bound star systems in the galaxy. Globular clusters are like the high-rise apartment blocks of the halo. Each one crams hundreds of thousands of stars into a region only a few tens of light years across. Their stars are generally ancient and metal-poor, meaning they formed early, before many rounds of supernovae had time to enrich the gas with heavy elements. Many globular clusters likely formed in the outer regions of the proto-galaxy. Others may have been brought in during mergers with dwarf galaxies, then captured and assimilated into the halo over time. The halo is also where the scars of past collisions show up most clearly. When a dwarf galaxy is torn apart, its stars do not instantly mix. For a long time, they trace out coherent streams and shells. In the Milky Way, we see these as arcs and ribbons of stars that share similar motions and chemical fingerprints. Andromeda's halo is even more dramatic, stuffed with clumps and streams that reveal a rich merger history. Triangulum, being smaller and more isolated, has a simpler halo, which tells us that even at this level, the internal structure of a galaxy records its social life. So far, we have talked about things we can see: stars, gas, clusters. Yet when astronomers map how stars move in galaxies, there is a problem. In a simple system where almost all the mass is in the visible disk and bulge, you would expect stars farther from the centre to orbit more slowly, the way planets in our solar system do. Instead, in galaxy after galaxy, the rotation speed stays high even in the outer disk, where there is little visible matter. It is as if an enormous invisible mass is holding those fast-moving stars in place. The most straightforward explanation is that galaxies are embedded in massive halos of dark matter. These halos are roughly spherical and extend far beyond the visible disk, often several times farther than the farthest bright stars. In the Milky Way, the dark matter halo likely contains many times the mass of all the stars and gas combined. The same is true on a larger scale for Andromeda. Even Triangulum, lighter and more fragile, sits in a dark halo that outweighs its visible parts. The stars and gas are like the frosting on a much bigger invisible cake. This dark halo shapes everything inside the galaxy. It sets the overall rotation speed of the disk. It determines how easily the galaxy can hold on to gas, driven outward by supernova explosions or by the fierce winds from active regions near the central black hole. It affects how satellites orbit and how strongly tides pull on them. When two galaxies approach each other, their dark halos are the first parts to touch, long before the bright disks overlap. The halos merge and mix, then the stars and gas respond to the new gravitational environment. Within the visible components, structure goes even further. Cold gas forms a thin layer within the disk, traced by radio observations of hydrogen and by millimeter observations of molecular clouds. Above and below the disk, warmer and more diffuse gas hovers in a thick layer, sometimes forming chimneys and bubbles where supernovae have punched holes through the denser regions. Beyond that lies a halo of hot gas, at temperatures of millions of degrees, detectable in X-rays and through its subtle effects on background light. All of this gas moves, cools, heats, and recycles through the galaxy over billions of years. Compare our three main local group spirals in this light, and patterns emerge. The Milky Way has a barred bulge, a two-layered disk, a moderately rich stellar halo, and a massive dark halo that has eaten several dwarfs. Andromeda is larger and perhaps more mature in some ways. Its bulge is bigger, its stellar halo more massive and clumpy, suggesting an even more active history of mergers. Its disk shows evidence of waves and ripples from past encounters. Triangulum, smaller and more gas-rich, has a more modest central region and a relatively clean disk, which may reflect a quieter interaction history so far. The key idea is that a galaxy is not well described by a single number, like mass or size. It is a nested set of components, each with its own geometry, age distribution, chemical makeup, and dynamic behavior. The bulge and bar tell you about early rapid formation and internal instabilities. The disk encodes billions of years of star formation and gas inflow. The halo records mergers and accretion. The dark matter halo defines the stage on which all of this unfolds. When we study galaxies in detail, we are reading this layered record. In the next part, we will take one of those layers, the stars themselves, and treat them as a kind of cosmic DNA. By measuring exactly which elements are present in which stars, we can reconstruct where they came from, how their host galaxies evolved, and even which long-dead dwarf galaxies were cannibalized to build the spirals we see today. By now, we have carved galaxies into bulges, disks, halos, and dark matter. That gives us the skeleton and the muscles. To understand the true history, we need the genetic code. In astronomy, that genetic code is chemistry. Each star carries in its atmosphere a record of what the universe was like when and where it formed. Read enough of those records, and a galaxy stops being just a pretty shape. It becomes a family tree. Start with one simple idea. The universe began mostly as hydrogen and helium, the two lightest elements. Everything heavier than that, from carbon in your cells to iron in your blood and gold in a wedding ring, was forged later inside stars and in the explosions that end some of their lives. Astronomers call all these heavier elements metals, even though many of them would not feel like metals in your hand. The fraction of a star's matter that is in elements heavier than hydrogen and helium is its metallicity. The first generation of stars had almost no metals at all. They were made from pristine gas left over from the Big Bang. When those massive first stars died, many of them exploded as supernovae. In those deaths, they created heavier elements and blasted them out into space, seeding the surrounding gas. The next round of stars formed from that slightly enriched gas. Each generation added more metals to the mix. As time went on, galaxies became more metal-rich on average. You can see this in our own Milky Way. The youngest stars in the thin disk, including the Sun, are moderately metal-rich. The older, thick disk stars tend to have lower metallicity and slightly different ratios of certain elements. Halo stars, especially the most ancient ones, can have metallicities hundreds of times lower than the Sun. They are like living fossils, preserving the chemistry of the universe when it was only a fraction of its current age. To measure this chemical code, astronomers take a spectrum of a star. That means spreading its light out into a rainbow and looking for dark lines where atoms in the star's atmosphere have absorbed specific wavelengths. Each element leaves its own pattern of lines. The depth and shape of those lines tell you how much of that element is present. With high-resolution spectra and careful models, you can measure the abundances of dozens of elements in a single star. Different kinds of supernovae and stellar processes make different mixes of elements. Massive stars that explode quickly tend to make a lot of oxygen, magnesium, and similar elements. Smaller stars that die more slowly, sometimes in white dwarf explosions, add more iron and certain other heavy species. If a galaxy had a rapid burst of star formation, and many massive stars exploded early, its older stars will have one pattern of element ratios. If star formation was slower and stretched over billions of years, iron from later explosions will change the pattern. This is why stellar chemistry acts like DNA. It is not enough to know that a star is metal-rich or metal-poor. The exact mix of elements is like a barcode telling you what kind of environment that star formed in. Two stars on opposite sides of the sky can share the same chemical fingerprint, revealing that they were born in the same long-vanished cloud, or even in the same dwarf galaxy before it was torn apart. This technique is called chemical tagging. Use this tool in the Milky Way and a striking picture emerges. Many halo stars with low metallicity and unusual element ratios do not match the typical pattern of stars formed in the main galaxy. Their chemistry looks more like what we see today in dwarf galaxies. Their orbits are also elongated and tilted relative to the disk. Put that together and you get a story. These stars were born in smaller galaxies that later merged with the Milky Way. When those galaxies were shredded, their stars were scattered into the halo, but kept their original chemical identities. Gaia, the space telescope that measures positions and motions for more than 1 billion stars, has turned this forensic work into a flood. It maps how stars move in 3 dimensions. Combine that with spectroscopic surveys that measure their metallicities and element ratios, and you can pick out whole families of stars that share a common origin. One such family, called Gaia Enceladus in the literature, appears to be the remnant of a substantial dwarf galaxy that merged with the Milky Way early on. Its stars have a distinct chemistry and a distinctive pattern of motions that cut through the disk. Andromeda offers a similar but even messier story. Its halo is full of streams and clumps. When astronomers measure the chemistry of stars in those structures, they find that many resemble the populations in its present-day satellites. This fits the idea that Andromeda has eaten many small galaxies over time. Some of the streams are enriched, suggesting they came from dwarfs that had extended star formation. Others are more pristine, with very low metallicity, pointing to early accretion events. The halo becomes a layer cake of past mergers. Triangulum, smaller and less experienced in the art of cannibalism, has a simpler chemical structure. Its stars show a more modest spread in metallicity and fewer obvious signatures of past major mergers. That contrast is useful. It shows how different growth histories leave different chemical fingerprints, even when the basic physics of star formation and supernova enrichment are the same. Chemistry does more than reveal past mergers. It also tracks gas flows within a single galaxy. In the Milky Way's disk, metallicity generally decreases as you move outward from the centre. The inner regions, with higher gas densities and more intense star formation over time, have processed more material through stars and supernovae. The outer disk, which has seen fewer stars and some infall of relatively fresh gas from outside the galaxy, remains more metal-poor. Subtle bends in this gradient can reveal when gas flowed inward or outward, or when star formation shifted from one region to another. Even the vertical structure of the disk is coded in chemistry. The thick disk stars are not only kinematically hotter, they also have distinct element ratios compared to thin disk stars of the same metallicity. That suggests a period early in the Milky Way's life, when stars formed rapidly in a more turbulent, heated disk, possibly stirred by mergers. Later, as things settled, a cooler, thin disk grew, with star formation proceeding in a calmer, more extended mode. The chemistry preserves that transition in a way that pure kinematics could not. Beyond chemistry, certain special kinds of stars help tie all of this to time. Variable stars like RR Lyrae pulsate in a regular way that relates to their intrinsic brightness. By comparing their true brightness to how bright they appear, astronomers can determine their distance. RR Lyrae stars are old, typically more than 10 billion years. Find them in a galaxy, and you know that galaxy has an ancient population. In the Milky Way and its satellites, RR Lyrae stars help map the three-dimensional structure of the halo and trace out streams from long-dead dwarfs. Other standard candle stars, such as certain types of red giants, help extend these measurements to Andromeda and beyond. Combine distance information with chemistry in motion, and you can build a detailed, time-stamped map of how stars are distributed and how they got there. It is like reconstructing the history of a city by sampling the building materials in every neighbourhood and reading the dates on the blueprints. What makes all of this so powerful is that stars are long-lived. A star like the Sun can shine for billions of years. Low-mass stars can last for periods longer than the current age of the universe. That means they remember. A star that formed when the Milky Way was young still carries the element ratios of that era, even if it has since wandered far from its birth site. By collecting and decoding these stellar stories, we can rewind the evolution of our galaxy and others without ever leaving the present day. In the next part, we will focus on the most dramatic stages of stellar life and death, and on the giant black holes that lurk at galactic centres. We will see how bursts of star formation, waves of supernovae, and the feeding habits of central black holes all feed back into the chemistry and structure of galaxies, shaping the very DNA we have just learned to read. Every galaxy is a story about how stars are born, live, and die. Yet at the very heart of many galaxies sits something that never shines on its own, a region where light itself can be trapped. Somehow these two things are tied together: the gentle glow of billions of stars and the lurking presence of a supermassive black hole in the centre. To understand the life of the local group, we need to understand how those cycles of star birth and death feed, shape, and are shaped by the monsters in galactic cores. Star formation begins in the coldest, darkest places. In the disks of galaxies like the Milky Way and Triangulum, giant clouds of molecular gas drift slowly through space, chilled to only a few tens of degrees above absolute zero. When spiral arms or other disturbances compress these clouds, Parts of them collapse under their own gravity. As the gas falls inward, it heats up, forming dense clumps that become protostars. Over time, these protostars ignite nuclear fusion in their cores and join the shining population of the galaxy. Most stars that form are relatively low mass and long-lived. They burn their fuel slowly and can shine for billions or even trillions of years. A small fraction are born massive, dozens of times the mass of the Sun. Those giants live fast and die young. They burn through their fuel in only a few million years, then explode as core-collapse supernovae. In those explosions, they scatter heavy elements into the surrounding gas and send shock waves rippling through their birth clouds, sometimes triggering new waves of star formation and sometimes blowing gas away entirely. If you zoom out, each galaxy has a characteristic star formation history. Some, often in dense environments or after violent mergers, burned bright early. They formed stars rapidly in the first few billion years and then faded, their gas exhausted or heated beyond easy cooling. Others, like many spirals, maintain a steadier pace, forming stars at a moderate rate over much longer intervals. Some experience bursts, sudden upticks in star formation, when fresh gas falls in or when a close passage with another galaxy compresses their gas. The Milky Way appears to be on the steady side. It has formed stars at a modest rate for much of its life, with some bumps when mergers stirred its gas. Triangulum, smaller but rich in gas, is more exuberant right now, with many bright star-forming regions. Andromeda may have had periods of intense activity in the past, and shows signs that its star formation has already declined from earlier peaks. These differences in star formation history affect everything from metallicity gradients to the brightness of spiral arms. Star deaths feed back into this story. Each supernova injects enormous energy into the surrounding gas, heating it, stirring it, and sometimes driving it out of the galaxy's disk into the halo. In dwarfs with shallow gravity wells, a few supernovae can clear much of the available gas, shutting star formation down for a long time or even forever. In larger galaxies, the gas may fountain out and then rain back down, recycling over and over. This stellar feedback regulates how quickly galaxies turn gas into stars. At the same time, deep in the centers of many galaxies, another kind of feedback engine waits. In the Milky Way, that engine is Sagittarius A star, a black hole with a mass of roughly 4 million suns. In Andromeda, the central black hole is much larger, probably tens of millions of solar masses. These objects are not cosmic vacuum cleaners, sucking in everything around them. Most of the stars in a galaxy will never come close. But when gas does wander near enough, or when stars are disrupted, the black hole can feast. As gas falls toward a supermassive black hole, it does not plunge straight in. It forms a swirling disk of hot material, orbiting just outside the point of no return. Friction and magnetic turbulence in this disk heat it to extreme temperatures. That hot gas can shine across the spectrum, from optical to X-rays. In some galaxies, this process becomes so luminous that the central region outshines the rest of the galaxy. Astronomers call such systems active galactic nuclei, powered by accretion onto a central black hole. These active phases are not constant. A galaxy can go through episodes of intense accretion separated by quieter periods. When the black hole is actively feeding, it does more than just shine. It also launches powerful outflows. Some of the hot gas is driven away in winds that rush outward at high speeds. In other cases, narrow jets of plasma shoot out along the black hole's spin axis and pierce through the galaxy into intergalactic space. Both winds and jets carry huge amounts of energy and momentum. This is feedback on a much larger scale than individual supernovae. In the biggest galaxies and in galaxy clusters, energy from central black holes can heat the surrounding gas enough to keep it from cooling and forming new stars. That is one leading explanation for why many massive galaxies today are full of old, red stars and show little ongoing star formation. Their central black holes turned on at some point, blasted the surrounding gas, and effectively choked off their own fuel supply and star-forming potential. In smaller galaxies like the Milky Way and Triangulum, the story is subtler. Our central black hole is relatively modest and currently quiet. It likely had more active phases in the past, but they were not energetic enough to strip the galaxy of its gas completely. Instead, stellar feedback and gas inflows from the intergalactic medium have dominated the regulation of star formation. Even so, evidence of past outbursts from Sagittarius A star shows up in giant bubbles of hot gas above and below the Milky Way's disk, relics of a time when our central engine was more lively. Across the local group, a striking pattern emerges. The mass of a galaxy's central black hole is closely linked to the mass of its central bulge of stars. Bigger bulges host bigger black holes. This suggests a kind of co-evolution. As gas flows into the inner regions and forms stars, some fraction of it also feeds the black hole. When the black hole becomes too active, its feedback can push gas away, slowing both its own growth and further star formation. Neither component completely controls the other, but their growth is intertwined. This interplay of star birth, star death, and black hole activity has been running for billions of years. It will also shape the future of the local group. In a few billion years, the Milky Way and Andromeda will begin their long-awaited collision. Their dark halos will merge first, then their disks will distort, fling out tidal tails, and trigger massive waves of star formation as gas clouds slam into each other and compress. The quiet suburbs of both galaxies will briefly become starburst regions. As the merger progresses, gas will lose angular momentum and spiral inward. That inflow will feed both central black holes, turning them into much brighter active nuclei for a time. Winds and jets from these active phases will blow out gas again, eventually helping to shut down the starburst. At the end of the encounter, the two supermassive black holes will themselves orbit each other, sinking slowly toward the center of the merged galaxy as they lose energy. When they finally coalesce, they will release a storm of gravitational waves, ripples in space-time that carry away energy at the speed of light. By then, the Earth may be long gone or unrecognizable, but any advanced civilization with sensitive enough detectors could, in principle, feel that distant tremor. It would be the final punctuation mark on a long chapter of intertwined growth, where star birth and death and black hole feeding shaped two galaxies and then fused them into one. In the next part, we will zoom back out to look at collisions and mergers from a larger perspective. We will follow the great rivers of stellar streams around the local group's big spirals and see how countless smaller crashes have built the galaxies we see today, long before the grand finale between the Milky Way and Andromeda. If you only ever saw pictures of galaxies on posters, you might think they live calm, solitary lives, each spiral floating quietly in the dark, minding its own business. That picture is wrong in a deep way. The universe builds its structures through collisions and mergers. The local group is not a static display shelf, it is a construction site where gravity never clocks out. The evidence is written all over the sky, but you need the right eyes to see it. In the Milky Way, for example, the halo is not a smooth glow of stars. It is laced with rivers and clumps. When astronomers map the positions and motions of halo stars using surveys from the ground and from space missions like Gaia, they see long, thin overdensities that wrap around the galaxy. These are stellar streams, the stretched-out remains of dwarf galaxies and star clusters that have been tidally shredded over billions of years. The Sagittarius stream is a famous example. It loops around the Milky Way in a great arc. Follow the stars in that stream backward in time, and they converge on the Sagittarius dwarf galaxy, which we met earlier as a satellite deep inside our halo. Each orbit, the Milky Way pulls more material off, feeding the stream. Over time, the dwarf is reduced to a faint remnant, while its stars become part of our halo. Other streams, like the one associated with Gaia Enceladus, trace older, more massive collisions that shook the early Milky Way and helped puff up its thick disk. Globular clusters also leave trails when they are stripped. The Palomar 5 cluster, for example, has long tidal tails that stretch across the sky. These slender streams are another piece of the same story. gravity constantly rearranges matter. Nothing stays in its original package forever. Even tightly bound clusters eventually leak stars into the halo as they orbit through the galactic potential. Andromeda shows this process on an even grander scale. Deep images reveal immense streams and shells of stars in its halo. One of the most striking features is the giant southern stream, a long ribbon of stars that swoops under the main disk. Other structures appear as arcs and clumps around the galaxy, each with its own chemistry and motion. Together they suggest that Andromeda has devoured many more sizable companions than the Milky Way has, or at least that it has done so in a way that left more visible debris. These streams are not just pretty, they are archaeological tools. Their shapes tell you about the orbit of the original satellite. Their thickness and degree of disruption tell you how long ago the stripping began. Their chemistry tells you about the galaxy or cluster they came from. By fitting models of tidal disruption to the observed streams, astronomers can also map the underlying dark matter halo, feeling its shape and clumpiness through how it stretches and bends the stellar rivers. This steady rain of small mergers fits into a larger picture of how the universe builds structure. The leading framework is sometimes called the hierarchical model. In this picture, small dark matter halos form first in the early universe. Gas falls into those halos, cools, and forms the first stars and small galaxies. Over time, gravity pulls those small halos together. They merge to form larger halos, which in turn merge again, building up a tree of growth where big structures are literally made from the pieces of smaller ones. Galaxies ride inside these halos. A large spiral like the Milky Way is not something that formed in one smooth collapse. It is the end product of many smaller galaxies falling in, merging, and sometimes being torn apart before they reach the center. Each merger event brings in new stars, gas, and dark matter. Sometimes the incoming system is so small that it contributes only a thin stream to the halo. Sometimes it is massive enough to shake the whole galaxy, thickening the disk or even transforming the galaxy's overall shape. In the language of this hierarchical universe, the local group is a node in a vast family tree. The Milky Way has its own merger tree, a branching history of all the systems that fell in and combined to make the galaxy we see today. Andromeda has another, likely even bushier tree. Triangulum, smaller and somewhat isolated, has a thinner record of accretion. The dwarf galaxies around them also have their own mini-trees, though many branches were cut short by environmental effects. Collisions are not only about small things hitting big things, sometimes the partners are comparable in mass. Astronomers call those major mergers. When two galaxies of similar size collide, the result can be dramatic. Their disks are distorted into long tidal tails. Gas clouds crash into each other, compressing and triggering intense bursts of star formation. Over time, the ordered rotation of the original disks is scrambled, and the remnant can settle into a more spheroidal shape. Many giant elliptical galaxies in clusters are thought to be the end products of such violent unions. Our own future is heading in that direction. The Milky Way and Andromeda are on a collision course. Right now, they are about 2.5 million light-years apart and moving toward each other at hundreds of kilometers per second. Gravity between them and between their surrounding dark halos is slowly overcoming the general expansion of the universe on that scale. In roughly 4 billion years, they will have their first close passage. Their disks will rip tidal tails from each other, flinging stars far into space. Over the next few billion years, they will swing around each other, losing energy to tides and to the motion of stars and dark matter inside them. Each encounter will bring them closer. Gas will flow inward, igniting bursts of star formation. Their halos will merge into a single, larger envelope. Eventually, the two galactic cores will coalesce into one new system, often nicknamed in popular writing as a combined name of the two galaxies. The exact final shape is still debated, but it will likely be more spheroidal than either original spiral. This sounds catastrophic, and on galactic scales it is. Spiral arms will be shredded. The night sky for any surviving planets will be filled with dramatic swirls of stars and glowing gas. Yet for individual star systems, the odds of direct collision remain tiny. Stars are so small compared to the distances between them that even in a galactic merger, most stars simply have their orbits rearranged. Our Sun may end up on a new path within the merged galaxy, but it is unlikely to hit another star directly. Still, the collision will change our cosmic address. The local group will go from being dominated by two separate big spirals to being dominated by one more massive galaxy, plus whatever remains of Triangulum and the dwarfs. Some of those dwarfs will have been swallowed already, others will be captured in the process. Stellar streams will multiply, new ones forming even as old ones are slowly mixed into a smoother halo. The merger tree will gain its last huge branch. Seen from far away, this whole process is just one example of the universe doing what it always does. Small structures forming first, then colliding and combining into larger ones. The local group is big enough for us, but it is just a modest participant in this cosmic assembly line. Clusters and superclusters carry the same story to even grander scales, where dozens or hundreds of Milky Way-sized galaxies have already merged and collided inside deep dark matter wells. The beauty of studying the local group is that we can see this hierarchical growth in detail. We can trace individual streams around the Milky Way and Andromeda, weigh their dark halos, and reconstruct their merger histories star by star. We can watch dwarfs being stripped in real time on cosmic scales and see others drifting in from the outskirts. Our neighbourhood is a laboratory where the general rules of structure formation are written in a script we can actually read. In the next part, we will step back from visible stars and talk about forces that do not shine. We will look at the seas of gas, radiation and magnetic fields that fill the space between stars and galaxies, and at the feedback processes that decide whether a galaxy keeps making new stars or fades into a quiet collection of stellar embers. When you picture a galaxy, you probably imagine stars first. Maybe glowing spiral arms, a bright core, some faint halo. Yet most of the normal matter in a galaxy is not locked up in stars at all. It is in gas, dust and hot plasma that flows through and around the galaxy like an invisible weather system. Mixed into that weather are radiation, magnetic fields and high-energy particles. Together they act as the quiet regulators of galaxy life. Start with gas, because gas is the raw material for new stars. In a spiral galaxy, gas exists in multiple phases at once. There is cold molecular gas in dense clouds, only a few tens of degrees above absolute zero. That is where stars actually form. There is warmer atomic hydrogen that fills much of the disk, a kind of interstellar medium in which those cold clouds are embedded. Above and below the disk there is hotter, more diffuse gas, sometimes heated by supernova explosions into bubbles that punch through the disk and vent into the halo. This gas is not static. It moves in giant circulation loops. Supernovae and stellar winds push gas out of the thin disk into the thicker layers above and below. There it can cool and fall back, like a fountain. Inflows from the intergalactic medium can add fresh, relatively pristine gas to the outer disk. Minor mergers with gas-rich dwarfs can dump additional fuel into the system. Over billions of years, a typical spiral galaxy breathes in and out many times, turning some of its gas into stars and recycling the rest. Radiation from stars is another invisible player. Massive young stars pour out intense ultraviolet light. That radiation ionizes nearby gas, stripping electrons from atoms and heating the surroundings. In dense clouds, this can carve out cavities and trigger complex pressure waves. In some regions, the waves compress nearby gas and help birth new stars. In others, they disperse clouds and shut down star formation. The balance depends on density, geometry, and timing. The same bright stars that mark a budding stellar nursery can also be the agents that end it. In galaxy clusters and groups, radiation does not stop at starlight. Hot gas between galaxies glows in X-rays, heated to tens of millions of degrees by the deep gravitational wells of clusters. When a small galaxy plunges through this hot medium, it experiences ram pressure stripping. Imagine driving through a heavy rainstorm with the windows down. The oncoming air and water would rip loose papers right out of the car. In the same way, the hot cluster gas pushes against the cold gas in the infalling galaxy and can sweep it out, leaving a wake of stripped material behind. Something similar happens, on a milder scale, to dwarf galaxies falling into the halos of giants in the local group. As they move through the extended hot gas that surrounds the Milky Way or Andromeda, their own gas feels a headwind. Combined with tidal forces, that headwind can peel off gas from their outer regions, especially in dwarfs with shallow gravity wells. Over time, the once gas-rich dwarf is left dry. Without fuel, star formation ceases, and the galaxy fades into a dim spheroidal with only old stars. Magnetic fields are subtler still. Every spiral galaxy we have studied has a large-scale magnetic field threading through its disk. The field is weak by everyday standards, far weaker than a simple refrigerator magnet, but it extends over tens of thousands of light years. These fields affect how charged particles move and can provide extra pressure that supports gas against collapse. That means they can slow down star formation by making it harder for gas to gather into dense clumps. At the same time, magnetic fields help guide cosmic rays, the high-energy particles accelerated by supernova shocks and other violent events. Cosmic rays add yet another component to the interstellar medium. They can heat gas, contribute pressure, and escape into the halo, dragging gas along with them. Recent simulations suggest that cosmic ray pressure can drive gentle but sustained winds out of galaxy disks, especially in low-mass galaxies, further regulating how quickly gas is turned into stars. All of these processes fall under the broad heading of feedback. Feedback is the response of a system to its own activity. When stars form rapidly, they produce more radiation, more winds, more supernova explosions, and more cosmic rays. Those outputs then push back on the gas, sometimes supporting it, sometimes ejecting it. If star formation tries to run away unchecked, feedback pushes it back down. If star formation drops too low, less feedback means gas can cool and gather again, allowing the rate to rise. In this way, galaxies tend to settle into self-regulated states. Environment tilts that balance. In the field, far from massive neighbours, a dwarf galaxy can slowly turn gas into stars, with feedback mostly coming from its own stellar population. In the halos of giants, the same dwarf is bombarded by additional external effects. Tides can strip mass. Ram pressure can remove gas. The hot halo can keep new gas from cooling and falling in. That is why many satellite dwarfs in the local group are quenched, meaning they have stopped forming stars, while similarly sized dwarfs in more isolated regions remain gas-rich and active. Even the largest structures feel the push and pull of feedback. In galaxy clusters, the central galaxies often host massive black holes that power bright radio jets. Those jets blow bubbles in the surrounding hot gas, seen as cavities in X-ray images. Without this energy injection, the gas would cool, flow inward, and form stars at rates much higher than observed. The fact that many central galaxies are red and dead, with little star formation, tells us that feedback from their black holes has been strong enough to keep the gas hot and stable. In the local group, we see more moderate versions of this balance. The Milky Way has giant lobes of hot gas extending above and below its disk, evidence of past energetic events either from the central black hole or from powerful star formation near the centre. Andromeda shows signs of complex gas flows in its halo, with streams and clouds traced by radio observations. Triangulum, less massive and more gas-rich, has weaker hot halos and more of its fuel still in the cold phase, which may help explain its active star-forming regions. The outcome of all these invisible forces is that galaxies do not simply use up their gas in a single burst. They pace themselves. Gas can be locked up for a while in warm or hot phases, then cool and return to star-forming clouds. Winds and outflows can remove gas from the disk, but deposit it in the halo, where it may eventually be reaccreted. Inflows from the cosmic web can top up supplies. Feedback from stars and black holes can throttle the rate, preventing runaway collapse. For a galaxy, survival is a negotiation between gravity, which always tries to pull matter together, and the various feedback mechanisms, which stir, heat, and sometimes expel that matter. In small galaxies, feedback and environment can easily win, shutting down star formation early and leaving behind faint relics. In larger spirals like the Milky Way, gravity has the upper hand, but still listens to feedback, resulting in a long, drawn-out history of star formation rather than a brief blaze. Understanding these invisible forces is crucial because they decide which galaxies go on forming stars for billions of years and which ones fade. They decide how many metals are produced and where they end up, in stars, in gas, or in intergalactic space. They shape the conditions for planet formation and for any potential life. In the next part, we will turn to the tools that allow us to detect and study all these subtle components from our small planet, from telescopes that see across the spectrum to experiments that catch ripples in space-time and ghostly particles flying through the dark. We have painted a rich picture of the local group: spirals and dwarfs, streams and halos, hot gas and dark matter. There is one obvious problem. From where you sit, on a planet wrapped in air and bathed in city lights, almost none of this is visible. So how do we know any of it is real? How do we spy on our cosmic neighbourhood from such an inconvenient vantage point? The answer is that humans have spent the past century turning the entire electromagnetic spectrum into a set of eyes and adding new messengers that do not use light at all. Start with the most familiar window, optical light, the kind your eyes can see. Ground-based optical telescopes collect far more light than your pupils ever could, using mirrors that are meters across. Long exposures reveal faint galaxies and star clusters. Careful imaging lets astronomers trace the shapes of spiral arms, the contours of tidal streams, and the outlines of dwarf galaxies. In the local group, optical observations resolve not just galaxies, but individual stars within them. You are not looking at smudges, you are looking at stellar populations, one sun at a time. Earth's atmosphere is both a blessing and a curse here. It protects us from harmful radiation, but it also blurs images and blocks parts of the spectrum. Adaptive optics systems on big ground telescopes can partially correct for atmospheric blurring by using deformable mirrors that adjust many times per second. Space telescopes take a more direct route. They get above the air altogether. The Hubble Space Telescope, for example, has taken deep images of regions in the Milky Way, Andromeda, and nearby dwarfs, resolving stars down to faint magnitudes and revealing details that would be impossible from the ground. Visible light tells only part of the story. Much of the gas in and around galaxies is cool or warm enough that it does not glow brightly in optical bands. To see it, astronomers turn to radio waves. Neutral hydrogen emits at a specific radio frequency, linked to a tiny energy shift in its ground state. Radio telescopes can tune to that frequency and map the distribution and motion of hydrogen gas across and around galaxies. In the local group, radio maps show extended disks of gas, streams trailing behind satellites, and clouds drifting in the space between galaxies. Arrays of radio dishes linked together act as a single giant instrument with sharp resolution. They can follow how gas flows along spiral arms, measure the rotation curves that reveal dark matter, and trace faint structures such as the Magellanic Stream. Even more sensitive instruments at millimeter wavelengths, such as large interferometric arrays, detect emission from molecules in cold clouds. That lets astronomers pinpoint where the densest star-forming regions are and measure how much raw material is available for future generations of stars. Infrared light adds another crucial angle. Dust in galaxies absorbs ultraviolet and optical light and re-emits it at longer infrared wavelengths. Regions that are completely hidden behind dust in visible images can glow brightly in the infrared. Space telescopes that see in these wavelengths can peer through dusty lanes in the Milky Way and Andromeda to study stars and gas near their centres. They can also pick out cool stars and brown dwarfs in the local neighbourhood, adding to the census of the faintest members of our galactic city. The newest generations of infrared observatories reach far into the spectrum, allowing them to detect the faint glow of old stars and the earliest galaxies at high redshift. For the local group, that means we can trace the light of very old stellar populations in dwarfs and in the outskirts of larger galaxies. Those faint halos, once invisible, become measurable. Combined with optical and radio data, infrared maps help complete the picture of how stars and gas are distributed in 3 dimensions. At higher energies, ultraviolet and X-ray telescopes open yet another window. Hot gas at millions of degrees shines brightly in X-rays. Observations in this band reveal bubbles and chimneys blown by supernova explosions, hot halos around galaxies, and the diffuse plasma in galaxy groups and clusters. In the local group, X-rays show the extended hot atmospheres of the Milky Way and Andromeda, and hint at how those atmospheres may be stripping gas from their satellites. Ultraviolet light traces young, massive stars and certain ionized gas features, highlighting regions of recent star formation and energetic feedback. Layer all these views together, and galaxies begin to look very different. The Milky Way is not a single, smooth disk. It is a network of cold molecular clouds, warm atomic gas, hot ionized outflows, and dust lanes, all lit by stars that span a huge range of ages and masses. Andromeda reveals a similar complexity. Triangulum, though smaller, shows bright star-forming regions in the radio and ultraviolet, wrapped in a more modest but still intricate structure of gas and dust. Light is not the only messenger. In the past decade, gravitational wave detectors have added a new way to listen to the universe. These instruments measure tiny distortions in space-time, caused by massive objects spiraling together and merging. So far, most detected events have been mergers of stellar mass black holes or neutron stars in distant galaxies, far beyond the local group. In the future, planned space-based detectors will be able to sense lower frequency waves from supermassive black hole mergers. A collision between the central black holes of the Milky Way and Andromeda, billions of years from now, would ring space-time in a way those detectors could hear across huge distances. Neutrino observatories add another layer. Neutrinos are nearly massless particles that interact only weakly with matter. They stream out of nuclear reactions in stars and out of supernova explosions. Detectors buried deep in ice or water can catch rare interactions when a neutrino hits an atom and produces a faint flash of light. So far, only a handful of astrophysical neutrino sources have been clearly identified, but as detectors improve, they promise a new view of star death and perhaps of exotic processes near black holes. Closer to home, missions like Gaia have revolutionized our map of the Milky Way. Gaia measures the positions, motions, and brightnesses of more than 1 billion stars with exquisite precision. That data turns the sky from a flat backdrop into a living, three-dimensional structure. Stellar streams, spiral arms, moving groups, and the warp of the disk all emerge from the patterns in those motions. Combined with ground-based spectroscopic surveys that provide chemical information, Gaia's map allows astronomers to trace the assembly of the galaxy in unprecedented detail. Large sky surveys on the ground flank this effort. Telescopes that scan huge swathes of sky night after night find faint dwarf galaxies, new streams, variable stars that act as distance markers, and transient events like supernovae. Algorithms sift through the data to pick out subtle patterns that would be invisible by eye. In this way, the census of local group galaxies keeps growing, especially at the low luminosity end, where human vision fails completely. From the outside, all of this can look almost magical. How can a faint smear of light on a detector tell you anything about stars, gas, dark matter, and cosmic history? The trick is that the universe obeys consistent physical laws. The way light is absorbed and emitted, the way gravity bends paths, the way gas flows and cools, all follow rules that we have tested in the laboratory and in nearby space. Telescopes and detectors are the senses. Physics is the grammar that lets us translate what they see into a story. The result is a kind of long-range empathy. From one small planet, with tools made of glass, metal, silicon, and frozen water buried underground, we have learned to feel the structure and motion of an entire galaxy group. We have mapped stars we will never visit, detected gas we will never breathe, weighed dark matter we will never see. In the next part, we will take this understanding and ask a bold question. If we can simulate all of this on supercomputers, can we reconstruct the past and predict the future of the local group? Or will the discrepancies between models and reality force us to rethink what we think we know about matter, gravity, and the universe itself? Imagine freezing the universe when it was very young, entering all of its properties into a colossal computer and pressing play. That is what cosmologists try to do when they simulate the cosmos. They build digital universes and watch them grow, hoping that somewhere inside those synthetic worlds, a structure appears that looks like our local group. If it does, we gain confidence that we understand the rules. If it does not, the mismatch becomes a clue that something in our picture of matter, gravity, or galaxy physics is incomplete. The starting point is the early universe as revealed by the cosmic microwave background, the faint afterglow of the Big Bang. That glow is almost perfectly uniform, but not quite. Tiny ripples in temperature reflect tiny ripples in density. Those ripples are the seeds from which all later structures grow. Cosmologists take a statistical description of those seeds, along with the measured amounts of dark matter, ordinary matter, and dark energy, and use them to generate an initial state for their simulations. In the simplest experiments, they include only dark matter. They fill a large virtual volume with many particles representing dark matter, each with mass and position. Then they let gravity act. Over billions of years of simulated time, those particles gather into clumps that merge into larger clumps. Filaments form where streams of particles meet. Voids open where little mass collects. The result is a digital cosmic web that looks strikingly like the real distribution of galaxies and clusters on large scales. To study galaxies, they need more detail. They add gas that can cool, heat, and respond to pressure. They add recipes for star formation, rules that say under what conditions cold, dense gas turns into stars and how quickly. They include feedback from supernova explosions and from accreting black holes, injecting energy and momentum into the gas. All of these processes happen on scales far too small to resolve directly in a large cosmological box, so they are modelled with simplified rules tuned to match certain observed properties of galaxies. From these ingredients, galaxies begin to appear in the simulations. Dark matter clumps become halos. Gas falls into those halos and forms rotating disks or puffy spheroids. Stars light up. Over time, simulated galaxy populations can be compared with observed ones. Do they have similar masses, shapes, and star formation rates? Do they show the right trends with environment? In many respects, the match is surprisingly good, which is a triumph for the standard picture of a universe dominated by cold dark matter and dark energy. The local group adds another layer of challenge. We do not just want a random spiral somewhere in the box. We want a pair of large galaxies with the right approximate masses and separation, each with its own set of satellites, all falling within a larger scale environment that resembles what we infer for our region of the universe. To get that, cosmologists use two strategies. One is to run huge volumes and then search for pairs of halos that look like the Milky Way and Andromeda. The other is to make a zoom-in simulation. In a zoom-in, they first run a coarse dark matter-only simulation to locate a region that will host a local group-like structure at late times. Then they rerun that region at much higher resolution, adding gas and all the extra physics, while keeping the larger scale environment in place but with less detail. This allows them to follow the growth of a digital Milky Way and a digital Andromeda, along with many dwarf galaxies and streams, without simulating the entire observable universe at that same fine level. Once these virtual local groups form, the comparison begins. How many satellites do the big galaxies have? How are those satellites distributed in space? How massive are their dark matter halos? How much star formation continues in them? Do the main galaxies end up on a collision course with roughly the right timing? Does the overall motion of the local group through space resemble what we infer from observations? Each positive match strengthens the model. Each discrepancy is an invitation to investigate. One famous tension is the missing satellites problem. Pure dark matter simulations predict that a Milky Way-sized halo should be accompanied by a very large number of small subhalos. For years, the number of known dwarf galaxies around the Milky Way and Andromeda was far smaller than the number of predicted subhalos. Improved observations have since revealed many more ultra-faint dwarfs, closing part of the gap. The rest may be accounted for if some small halos never manage to form stars, remaining dark. Simulations that include gas physics and feedback naturally produce many dark or nearly dark halos, but the exact numbers and properties remain an active test. Another tension lives in the inner structure of dwarfs. Simple cold dark matter simulations tend to produce halos whose density rises steeply toward the center, a shape astronomers call a cusp. Some observations of dwarf galaxies, including some in the local group, suggest flatter central density profiles, more like cores. One proposed solution is that repeated bursts of star formation and supernova feedback can stir the central gas and dark matter, transforming cusps into cores. Simulations that include very energetic feedback sometimes produce such cores. Others argue that this requires fine-tuning and that perhaps dark matter itself has additional properties, such as self-interaction, that change its behavior in dense regions. There are also puzzles about the spatial arrangement of satellites. Around both the Milky Way and Andromeda, many dwarf galaxies seem to lie in thin planes and, in some cases, appear to share similar orbital directions. In a naive picture, you might expect satellites to be arranged more randomly around their hosts. Some high-resolution simulations find that groups of satellites can fall in along filaments, naturally forming partial planes. Others suggest that the observed alignments are unusually strong and therefore a potential challenge to the simplest versions of the model. The debate continues, with new data and more detailed simulations sharpening the questions. Through all of this, the simulations are not just truth machines, they are also laboratories. Researchers can switch off certain processes, such as strong feedback from black holes, and see what changes. They can make the gas more or less efficient at forming stars. They can experiment with different dark matter properties. When a particular combination reproduces several independent observations at once, it gains credibility. When no version of the standard physics works, that failure points toward the need for new ideas. The local group is a particularly powerful testing ground because we have such detailed observations of it. We know the masses of its major galaxies, the orbits of many of its satellites, the chemical compositions of stars in its halo streams, and the rough shape of the surrounding large-scale structure. Any digital local group that claims to be realistic has to pass many simultaneous tests. It is not enough to match one number. The pattern of galaxies, their internal structures, and their histories all need to make sense together. There is something quietly profound about watching a simulated universe evolve on a screen. Tiny initial ripples grow into filaments and knots, then into galaxies and groups. Somewhere in that evolving pattern, if the physics is right, structures like our local group emerge as an almost inevitable consequence of the initial conditions. If the physics is wrong or incomplete, the digital universe grows into something that looks subtly or glaringly different from what we see. Either way, the exercise teaches us something. In the next part, we will step out of the computer and back into cosmic time. We will trace the local group from its first stirrings, in the era when the universe filled with the light of the first stars, all the way into a far future when cosmic expansion will hide almost everything beyond our merged group from view, leaving our descendants in a very different-looking universe. So far, we have treated the local group as something you can map in space. Galaxies here, streams there, dwarfs drifting on the outskirts. Now stretch that picture out a long time. The same galaxies have not always looked the way they do now, and they will not keep their present shapes forever. The local group has a past written in ancient starlight and a future shaped by dark energy. In this part, we will walk that path from the era when the first galaxies lit up the universe to a far future when almost nothing beyond our merged group will be visible. Wind the clock back to when the universe was only a few 100 million years old. At that time, space was filled with mostly neutral hydrogen gas. There were no grand spirals, no rich clusters, only small protogalaxies forming in the first dark matter halos. Massive stars were switching on for the first time. Their ultraviolet light began to carve bubbles of ionized gas around them, regions where electrons were stripped from hydrogen atoms. When enough of these early galaxies ignited, their bubbles overlapped and the entire universe went through what we call the epoch of reionization. During reionization, tiny galaxies mattered enormously. Many of the first sources of ultraviolet light lived in small dark matter halos. They were efficient at letting radiation leak out into the surrounding medium. In the local group today, some of the ultra-faint dwarfs appear to be direct descendants of those early systems. Their stars are almost all ancient and extremely poor in heavy elements. Their star formation histories show a brief flash of activity more than 12 or 13 billion years ago, followed by a long silence. They look exactly like galaxies that formed stars before and during reionization, and were then shut down by that rising ultraviolet background. The larger progenitors of the Milky Way and Andromeda also lived through this era, but with deeper gravity wells. They continued to pull in gas and form stars, even while smaller neighbours were quenched. Over the next few billion years, many of those early dwarfs fell into the growing halos of the bigger galaxies. Some were torn apart completely, their stars now part of halo streams and diffuse envelopes. Others survived as satellites, still orbiting today and still displaying the ancient chemistry they acquired before the universe was fully ionized. As time went on, the local group emerged from this early turbulent youth into a more structured adolescence. Gas continued to flow along filaments into the main dark matter halos. Disks grew, bulges formed, mergers stirred the pot. At around half the present age of the universe, the Milky Way and Andromeda were smaller, but already recognizable as spirals. Dwarfs orbited them in growing numbers. The larger scale environment was becoming more defined as well, with the Virgo cluster and other concentrations of mass deepening their gravitational wells and beginning to pull on our group. Then a new player started to dominate the long-term story: dark energy. At early times, the universe was dense enough that gravity slowed the overall expansion. On large scales, everything was still moving apart, but the rate of that expansion was decreasing. A few billion years ago, the balance tipped. The average density of matter dropped as space expanded, while dark energy, which acts like a constant energy density of empty space, did not dilute in the same way. Eventually, dark energy began to drive an accelerated expansion. On human timescales, that acceleration is gentle. On cosmic timescales, it changes everything. Structures that are already gravitationally bound, like the local group, remain intact. The mutual gravity of the Milky Way, Andromeda, Triangulum, and the dwarfs is enough to hold them together against the general stretching of space. Larger scale structures that are only marginally bound may fall together more slowly or never complete their collapse. Galaxies that are not bound to us are carried away faster and faster by the expanding fabric of space. Project this into the future. Today, light from very distant galaxies still has time to reach us, though it arrives stretched to longer wavelengths by the expansion. As acceleration continues, there will come a time when light emitted by most galaxies beyond our immediate region will never reach the local group. They will cross what is called a cosmic event horizon, a distance beyond which events are forever out of causal contact with us. In rough terms, give the universe on the order of 150 billion years, and almost everything beyond the merged remnant of the local group will have slipped permanently out of view. Long before that, closer dramas will play out. In a few billion years, the Milky Way and Andromeda will begin their merger dance, as we described earlier. Triangulum may be drawn in as well, either merging with one of the giants along the way or joining the final remnant. Many dwarfs will be swallowed, others will be flung into new orbits around the merged galaxy. The local group will reorganize itself, with one dominant massive galaxy at the center and a retinue of surviving dwarfs and streams in its halo. After the merger settles, star formation will continue for a long time, but likely at a declining rate. Some gas will be used up in the starburst triggered by the collision. Some will be heated and blown out by supernovae and black hole feedback. Some will fall back and recycle, fueling more gradual star formation over billions of years. Eventually, however, the supply will run low. Fresh infall from outside will diminish as the cosmic web thins and as the merged halo consumes or expels what remains inside it. Over tens to hundreds of billions of years, star formation across the local group will taper off. Giant blue stars will always live and die quickly, so they will vanish first. Redder, longer-lived stars will dominate. Stellar populations will age. The night sky on any surviving planet will grow redder and dimmer as the last massive stars fade. New stars will still form here and there in pockets of remaining gas, but the overall trend will be toward a universe where most of the light comes from old stars and the embers of former generations. On even longer timescales, the main actors will change again. White dwarfs, neutron stars, and black holes will make up an increasing fraction of the stellar population. Many of the stars that survive will be small red dwarfs, capable of shining for trillions of years. They will outlive almost everything that seems important to us now. Planetary systems will continue to orbit, though close encounters over vast spans of time may scatter some planets into interstellar space and send others plunging into their stars or remnant companions. Meanwhile, the rest of the universe will continue to recede. Any future astronomer living inside the merged local group remnant, hundreds of billions of years from now, will see a very different sky than we see today. Almost no external galaxies will be visible. The cosmic microwave background will be cooled and stretched beyond easy detection. Without careful theory and indirect clues, it will be much harder to infer that the universe once teemed with galaxies and that space itself once expanded from a hot, dense beginning. This is one of the strangest implications of our modern picture. We live at a special time, not because the universe cares about us, but because the physics of expansion and structure formation happens to make this era unusually informative. Enough time has passed for galaxies, groups, and clusters to form, but not so much that accelerated expansion has hidden most of them from view. We can still see out to the cosmic microwave background, still detect galaxies at many stages of evolution, still read the merger histories in the halos of our neighbours. The local group is a perfect lens for this perspective. Its faint dwarfs preserve the conditions of the early universe. Its big spirals embody billions of years of star formation, feedback, and mergers. Its future collision and eventual isolation illustrate what dark energy will do to bound structures. When you trace its story from reionization to the far future, you are not just learning about a handful of galaxies near the Milky Way. You are watching the full arc of cosmic time play out on a stage you can actually study in detail. In the final part, we will bring this long journey back to the personal scale. We will ask what it means for a species on a small world to find itself in this particular neighbourhood at this particular moment, and how this cosmic context might reshape our ideas of home, meaning, and responsibility in a universe where even galaxy groups have life stories. We have spent a long time wandering through the local group. We have watched galaxies collide, dwarfs torn apart, dark matter halos tangle, and stars live out their brilliant, complicated lives. At some point, a simple thought creeps in. Where do we fit in all of this? Not as a galaxy or a halo, but as a species on a small rock orbiting one very ordinary star in one spiral arm of one galaxy in this modest group. What does it mean to be alive here and now in this particular neighbourhood of the universe? Start with the numbers, because they are both grounding and dizzying. The Milky Way likely holds a few 100 billion stars. Andromeda holds perhaps several 100 billion more, maybe close to 1 trillion. Triangulum adds tens of billions. The dwarf galaxies sprinkled through the local group add still more, though their contributions are modest by comparison. Telescopes and missions that hunt for exoplanets have taught us that planets are common. Most stars probably have at least one. Many have whole families. Take sun-like stars and smaller red dwarfs, the most common kind of star in the universe. Observations suggest that a significant fraction of them host rocky planets in or near their habitable zones, regions where liquid water could exist on a surface under the right conditions. Even if only a few % of suitable stars in the Milky Way have such planets, that still means billions of potentially habitable worlds in our galaxy alone. Extend that logic to Andromeda, to Triangulum, and to the more substantial dwarf galaxies, and you arrive at a staggering possibility. The local group may contain tens of billions of planets where chemistry could someday learn to call itself biology. Of course, a planet that could host life is not the same as a planet that does. The step from chemistry to cells, from cells to complex organisms, from organisms to technological civilizations, may be rare or common. We simply do not know yet. Our sample size of 1 is comically small. Still, when you imagine the local group as a cluster of cities rather than just a few glowing spirals, the question becomes more pointed. Are we the only minds in this entire multi-galaxy town? Or are there other species looking up at their own skies, wondering about us without knowing we exist? If intelligent life does arise elsewhere in the local group, it will live under different skies, but much the same physics. Beings in Andromeda would see a huge Milky Way glowing in their night sky, much as we see Andromeda as a faint smudge in ours, only brighter. They would watch their own dwarf satellites being stripped and scattered. They would map their own halo streams and infer their own merger history. Their telescopes would pick out a spiral galaxy 2.5 million light-years away and eventually realize it is not a cloud, but a vast city of stars. Communication across such distances would be slow. Even at the speed of light, a message from the Milky Way to Andromeda would take millions of years to arrive. By the time any reply came back, continents could shift, languages could die, entire civilizations could rise and fall. In that sense, the local group is too large to be a conversational neighborhood in any human sense. Yet it is small enough that a truly long-lived species, or a network of automated probes, might eventually explore parts of it over timescales that make human history feel like a blink. Whether or not anyone else is out there, the very act of understanding the local group changes how we see ourselves. For most of human history, the universe seemed limited to the Milky Way and perhaps a little beyond. Bright fuzzy objects like Andromeda were recorded as nebulae, clouds in our own galaxy. The cosmic yardstick was short. The scale of everything was compressed into what we could see with unaided eyes and small telescopes. Our sense of home stopped not far beyond the stars we could name. The turning point came when astronomers learned to measure the distances to those fuzzy objects. By using variable stars in Andromeda and comparing their true brightness to their apparent brightness, Edwin Hubble and others showed that Andromeda is far outside the Milky Way. It is another galaxy entirely. That realization, often called the Great Debate in hindsight, was not just a technical shift, it was an existential one. The universe suddenly grew from one island of stars to many islands scattered across vast distances. The Milky Way went from being the universe to being one city among many. From there, the picture kept expanding. Better telescopes revealed more galaxies. Radio and infrared instruments uncovered gas and dust. X-ray and ultraviolet instruments showed hot plasmas and violent processes. Sky surveys and space missions mapped the distribution of galaxies on larger and larger scales until the cosmic web emerged. Simulations and theory tied that web back to ripples in the early universe. Along the way, our local group went from being a vague cluster of nearby fuzzy patches to a well-mapped family of distinct galaxies with names, masses, orbits, histories. Seeing ourselves as citizens of the local group is a natural next step. It means recognizing that our story is not just Earth, not just the solar system, not just the Milky Way. Our long-term fate as a civilization is tied to the fate of the galaxies around us. Their gravity binds us. Their past mergers enriched the gas that formed our sun and planets. Their future collision will reshape the night sky for any descendants we might have. In a very literal sense, our address includes not only a planet and a star and a galaxy, but a group. This wider address does not make humanity insignificant. It changes the shape of significance. A single human life is fragile and brief. A single civilization is fragile and brief. Yet the fact that matter in this particular galaxy group has organized itself into beings that can reconstruct the story of the whole group is extraordinary. We are made of atoms forged in ancient stars that lived and died long before the Milky Way had its current form. Those atoms have spent billions of years riding through mergers and tidal streams, through halos and disks, only to end up in brains that can wonder about their own trajectory. There is also a sense of responsibility that comes with this knowledge. On the scales that matter to our daily lives, the universe is indifferent. Asteroids do not care who they hit. Supernovae do not ask permission. Yet on the scale of the local group, we may be, for now, one of the few, or possibly the only species capable of understanding and preserving the story of this place. If we erase ourselves through neglect or short-sightedness, the universe will continue, but a unique way of the universe knowing itself will be gone. You can think of the local group as an immense library written in stars, gas, and dark matter. Every dwarf galaxy is a chapter about the early universe. Every halo stream is a sentence about ancient mergers. The Milky Way and Andromeda are long, complicated narratives about how large galaxies grow. Our species is one paragraph in one page of one of those volumes. We are also, if we choose to be, the librarians. We are the ones who can read the pages, compare them, and pass their meaning on. The strange gift of this moment in cosmic time is that the library is still open and well lit. The cosmic microwave background is still detectable. Distant galaxies are still visible. The local group is still in the middle of its life story, not yet merged into a single remnant. We have access to chapters that future observers may find much harder to read. To live now is to exist in a window when the universe is big, bright, and legible. So when you next look up at the sky, imagine everything we have just explored compressed into that view. Not just stars, but an entire layered structure of galaxies, groups, and flows of matter. Somewhere in that structure are billions of other planets, many of them lifeless, some of them perhaps waking up to their own awareness. Somewhere in that structure is a future where our galaxy has merged with its neighbour, and where the local group has become a solitary island in an accelerating universe. We do not know how far our own story will reach into that future. That uncertainty is part of what makes it ours. What we do know is that we have already come far for a species that learned about the sky by drawing constellations and telling stories around fires. Now we write new stories, with telescopes and equations, with simulations and data. But the core is the same. We are trying to understand where we are, how we got here, and where we might go next. In the end, the local group is not just an arrangement of galaxies. It is our cosmic neighbourhood, our extended home. To know it is to know ourselves a little better. To see its past and future is to place our own brief existence in a much longer, richer narrative. And to feel, even for a moment, that we are part of that narrative is one of the deepest kinds of meaning a small, thinking creature on a small, bright world can find.